Rispondi. Chi? Chi?
Cosa?
Chi?
Che cosa?
No, ti vedo un po'.
Ah, no, pensavo a...
All'infinito.
Sì, l'universo è tutto quanto. No, pensavo che non c'è ancora nessuno, dico, ma vabbè. È presto, è presto.
Sì, questo che stavano mangiando giù.
Ah, ecco. Sì, sì, vabbè, perché è un orario un po' strano, effettivamente.
Non è perfetto.
Sì, perfetto perché così non perdi tempo perché usi la pausa pranzo, però il pranzo ti rimane qua.
Io non so mai.
Ah, ok, quindi facile. No, io non ce la farei.
Non ce la fai.
Si vede che non ce la farei.
No. Pensi di essere sovrappeso?
Sì, no, sono a dieta da 5-6 mesi.
E? Funziona?
9 anni. Avendo problemi di tiroide, tutto più rallentato.
Ah, ovviamente, sì. Io ho un fratello che ha un problema anche questo. Vabbè, nessuno nasce perfetto.
Meno male.
A Cecilia sei in giro.
Cecilia Azzoni? No, oggi no, credo, perché credo abbia avuto problemi a tornare, non era... è andata a casa.
E dov'è lei?
Massa.
Massa.
E da quello che so non ha trovato il ritorno in tempo, quindi ciao. Poi non so, magari ci stupisce, ma stamattina dovevamo fare lezione e è stata connessa telematicamente, quindi non è qua. Sì, sì, abbiamo il corso di mattina attiva adesso.
Ciao. Sei già pronto? Vado a prendere i fogli di esame e poi possiamo cominciare.
Leggi bene. NASA. NASA. NASA.
Scienza guarda.
Scienza guarda. Va bene.
Io avevo un maggiore supplemento, non ho potuto pensare alla quantizzazione.
Posso filmare intanto l'altro? Stiamo aspettando.
Io penso che lo faccio. Non so se avete Laura, svegliati, non importa.
Ah, no, ma sì.
Ma lo sapevi che era touch sto coso?
Sapete che?
Che era touch? Che touch?
Stai scherzando?
Cioè, sono arrivata stamattina, cioè, da paura, era anche un tablet, ha detto. Cioè, se lo pieghi ci disegni su. Cioè, adesso lo scopro sta cosa, l'ultimo giornata.
Chissà quanto sarà costato. Bella sta roba.
Interessante.
Allora, iniziamo.
Non so. Ma aperte tutte Martina, non so se c'è un motivo.
Se lo fa Martina ci sarà un motivo. Vabbè. Cominciamo?
Iniziamo prima finiamo.
Ok.
Va da solo?
Eh?
Va da solo? Dice Martina va da solo, però non vedo che lampeggia.
È a posto, ma non devi lampeggiare nulla.
Ok.
L'unica cosa, ecco, stai lì.
Sì, sì.
Il microfono lo tiriamo qua. Ok. Good afternoon to everyone. So, today we have two speakers. Our first speaker is Eleonora, and she's talking about exomoons. So,
Yeah. Hi everyone, for my last journal club I'm going to talk about the exomoon and their detection around directly imaged exoplanets. This paper was inspired by the paper that came out last year by Tichy, Kippin and Smith about a claim of a candidate exomoon in around Kepler 1625b. So they discuss essentially in this paper how feasible it is to detect an exomoon right now and how it should be in the next years as soon as the new instruments arrive. First of all, we need to understand that the exomoon detection is based on second order signals, which are on top of the Keplerian first order signal of the planet itself that orbits the star. So the proposed methods up to now are, of course, measuring the photocenter motion of an unresolved planet-moon system, but it could be, as I said, it could be difficult because you cannot distinguish the planet from the moon. You can also detect the transit of self-luminous planets in front of which the moon transits. You can also observe change in the polarization signatures of the most massive planets. Or for example, the most important method that could be applied also for planetary system, and that it was also applied when detecting TRAPPIST-1, is the TTV, which is the transit timing variation. And that's the main method that characterized the paper that claimed the detection of the exomoon. As we can see in the picture, you see there's a variation in the transit, both in the depth and in the duration of it, because of this potential exomoon that's crossing the planet. But in this paper, the method that could be most efficient should be the radial velocity monitoring of directly imaged exoplanets. So, what are all the signals that you should expect to receive when observing planetary exomoon system? First of all, that's the right period and the right signal that you should measure. That's the motion from the exomoon itself, which is a Keplerian motion, and we can see here from the first equation that it depends from the period of the moon, its eccentricity, its mass, and its inclination with respect to the line of view, and as well the mass of the planet MP. But for circular orbits and normal moons, which is the mass of the moon is very small compared to the planet, you can approximate to the second equation, which is simpler. And for Kepler 1625b, first, the moon, the signal should be around 200 meters per second. But this, of course, is overlapped to the higher signal, which is the orbit of the planet around the star, which is a Keplerian 2, and it is well known, nearly the same equation, and for this system it should be around 33 kilometers per second. But there are also other effects that can cause a signal that you detect. First of all, for non-luminous planets, which are the oldest planets that you observed, you have generally some sort of phases as they orbit around the star. So you have a different illumination of the planet, which can be mapped with a phase function. If you think of the planet as a Lambertian sphere, which emits isotropically all around the surface and on the space, you can have this phase function. And if you think of a planet which is nearly a John, you can have a signal, which is the last expression here, which depends on the equatorial velocity of the planet and the sine function. This, of course, cannot happen, or could not happen possibly, if you have a different line of sight, a different inclination. So you can have various signals provoked by this effect, and these also depend on the angle that you have between the rotational, the axis of rotation of the planet and the spin axis of the planet and the line of sight. So these are very different signals that you could possibly detect, and in particular, the last equation corresponds to the bottom right graph, which is some sort of discontinuity in the spectrum, but you could not possibly see it in general because there are so few photons to measure that kind of that part exactly. So you won't possibly be able to measure it. But in any case, this is a kind of a small signal compared to anything else that's happening. Another velocities is nevertheless the planetary activity, which is nearly the same as what happens for the stars. You know, when you observe a star and you want to measure the radial velocities of it, you can possibly have a false positive due to the fact that the star is active, as it could have spots, faculae on everything else that could mimic the transit of a planet or the shift caused by a Keplerian motion, but that is not the case. This could happen also on self-luminous planets that show clouds, for example. So there are kind of different spots that could mimic the presence of a moon, which is not there. For this particular process, they modeled with an algorithm, and they explained loads of it in the appendix of the paper. They modeled, they reproduced the curve of Neptune, which is the top panel of this graph, and you see that these are data actually. These were acquired within the K2 mission, and they were simply stretched in order to simulate a planet, an exoplanet with 18 days a period instead of the real period of Neptune. Then, on the bottom part of the graph, they simply try to reproduce with the algorithm the same effect that you would have when observing not Neptune, but an exoplanet with a Jupiter mass. And this could be the signal that you should observe. Nevertheless, you see more or less, I don't know, 50 or maybe 100 meters per second, which is negligible with respect to the other signals that you see. This is an important process that happens, which is the peak polling by the exomoons. So you should picture this moon and this planet that was claimed, Kepler 1625b. The planet is more or less one Jovian mass, while the moon is more or less one Neptune mass. So if you do the brightness ratio between the planet and the moon, you obtain a ratio which is fairly high. So when you observe a planet without knowing there's a moon in it, you observe part of the light that comes from the moon, whether it is reflected if the moon is cool, or self-luminous moons, which could potentially happen in other exosystems. So when you measure a radial velocity, you measure a contribution higher or lower, depends on the situation, due to the presence of the moon itself. And if you don't know it, you should receive very different signals with respect to what you should expect from a star-planet system. This is particularly important for conjunctions between the planet and the moon. So the last effect that they model is the disk clamp occultation. Some young systems with stars and self-luminous planets have still have the disk from which they formed, and this disk could have clamps in it. These clamps could be thick sometimes. So if they cross the line of sight from the planet to us, they should mimic the presence of a moon. They could mimic the presence of a moon, and they gave an estimate of what this should be with respect to the signal that they should expect. And then the last equation, you see the form of the signal that you should detect. And this is also about 10 to 50 meters per second, so it should be no problem, I guess, in their framework, in their imagination framework that they are discussing. This is the summary of all the signals that we've seen. So in black you see the final signal that you should detect when studying system star-planet moon, and this could be what essentially you should detect when observing the radial velocities amplitudes. So they discussed briefly the feasibility of these detections, and they simulated the observation of Beta Pictoris b, supposing it has a moon, Neptune-like moon, just like Kepler 1625b does. And they discovered that, nevertheless, this is a photon-limited problem, and you should, for increasing the quality of the observation, you should increase the bandpass of your instrument. And of course, you probably would like to apply adaptive optics and coronagraphy techniques to improve the quality of what you're observing. Or if they estimate a gain of a factor nearly 10, and they think that next generation of instruments could be able to detect such moons. So, discussion and conclusion, they suggest that a survey of radial velocity could be helpful for detecting exomoons, not only for the idea of the exomoon, which could be very different from the moons of our solar system, and that could put again into discussion all the theories of planetary formation that are currently, or they are already being discussed. Also, the detection of a survey of radial velocity could improve our knowledge of the period of the planet as well as the obliquity of the planet, and one could have very much more like Uranus-like planets. And you should also have news about information about what's in the atmosphere, this is the part I'm most interested in because of what I do in my PhD. So, in short, what they did was to try and have a simulation of all the processes that could happen when studying an exomoon, when trying to detect an exomoon, and they considered that the presence of an exomoon could be potentially revealed by our instruments and the next generation ones. So, I'm done. This was my last Junior Club, and I thank you all for the attention.
Thank you, Leonora. Questions?
I don't think you have to wait for the next generation of telescopes, because I don't know if you maybe haven't followed all the detection methods carefully, but at the Wind telescope, they're building, NASA is building this super precise spectrometer that will detect, I think, 30 meters per second or something like that.
Yeah, but they consider that as a next generation, that too, because they are not actually.
The telescope exists and the instrument is almost ready. It's going to be
Yeah,
very soon.
The thing is that this paper shows, in my view, there's nearly too much optimistic for this. They say we are able to observe them right now, so okay, let's go and observe. But it's not so easy right now, and I've discussed that.
We're almost there.
Yeah, we are so close. That's why I wanted to.
Months, maybe. I don't know how to explain it.
Let's hope it finds something else. Yeah.
So you're aware of this instrument?
Yeah. I know that they quoted also SPHERE, which is actually an imager and a spectrograph, which is already in use, and they say it's potentially able to detect this.
I don't know, but the new spectrograph, of course.
Yeah, for sure.
I was just curious, simulation includes just one exomoon, or like reality much more than
No,
one
within the system of a planet, you mean?
Yeah.
No, just one. At most, I think that they consider just one moon because they detected just one, and they wanted to reproduce this particular system, trying to generalize, but they're
exomoon?
still.
Reality would be much more complex.
Of course, but I don't know if we would.
Planets have a lot
Yeah.
of-
Yeah.
Okay. Thank you very much. Hai la chiavetta?
Sì.
Perfetto.
Posso usare il mouse per il computatore?
Abbiamo scoperto che questo affare è touch, quindi
Ah,
stiamo anche.
sì. La prima, Journal
Prima.
Card Press.
Questa?
Sì.
Era proprio qua perché altrimenti... Ok. Vai, metti pure schermo. Ok,
E
so,
così
se provi... Vai, metti pure.
così. No, ma intendevo come, cioè, per, tipo, come puntatore per far vedere parti dei plot.
Ah, allora usiamo.
No, uso il mouse. Ok. Perfetto.
So, our second speaker, Virgilio, is going to talk us about stellar ages and galaxy shapes. 10 minutes.
Thank you. Good morning, everyone. Today I'm presenting this paper from Van de Sande about the relation between the stellar age of a galaxy and their intrinsic shape. So, in order to study how galaxies build up their stellar mass and angular momentum, we have to investigate both the stellar population and stellar kinematics. In fact, the stellar age can tell us when stars were formed in a galaxy, but not how. While the stellar kinematics can help us to say something about the change in angular momentum and the orbital distribution of stars due to merger, but is not able to distinguish the contribution, for example, of major mergers. Thanks to large integral field spectroscopy surveys, now is it possible to connect the galaxy star formation and merger history on the same physical scales over a large range in galaxy mass, morphology and environment. In this paper, the author used the SAMI galaxy surveys in order to present the first study of spatially resolved stellar kinematics and global stellar population in a wide sample of galaxies. Their main result is that the existence of a correlation between the stellar population age and the location of the galaxy in the velocity over sigma ellipticity diagram, which link the ordered motion to random motion to the observed ellipticity. And so they found out that stellar age follow the intrinsic ellipticity. They obtained the galaxy parameters such as the effective radii, ellipticities and position angles, applying a multi-Gaussian expansion technique. The spatial resolved stellar rotation and stellar velocity dispersion fit in the spectra with the penalized pixel fitting code. They obtained a global stellar population luminosity weighted age using some of the leak indices, and they obtained stellar masses using a color mass relation. And they apply this analysis to about 800 galaxies with a broad range in stellar mass, morphology and environment. In this plot you can see their stellar kinematic measurement. They plotted the velocity over sigma, which is the ratio between the ordered rotation to the random orbital motion, and it is defined as the square root ratio between the luminosity weighted square velocity and square velocity dispersion measured in an ellipse which encloses half of the total projected light of the galaxies versus the stellar mass. And the plot is color coded with the age of the galaxy. They noted a strong relation between the ratio, the velocity over sigma ratio, and the age of the galaxies. Young stellar population, which are in blue, are predominantly located in rotationally supported galaxies, while all stellar populations in red are more located in galaxies that are pressure supported by the random motion of their stars. In order to investigate more in depth this relation, they also plotted the relation between age and stellar mass and age and velocity over sigma. In pink you can see the early type galaxies, while in green you can see the late type. And They found a relation between age and velocity, a strong relation between age and velocity over sigma, but still both the relations show residuals. Here you can see the main result of this analysis. That is the velocity over sigma and the ellipticity diagram. On the left part you can see the galaxies are color-coded by the ages, and they used different symbol size to define different galaxy masses. On the right, they used a locally weighted regression algorithm to recover the mean underlying trend of the sample, and they also plotted the theoretical prediction obtained from the application of the tensor virial theorem. The magenta line represents the behavior of an axisymmetric oblate rotating spheroid with varying intrinsic ellipticity and anisotropy observed edge-on. In this line, we can find flat rotating supported galaxy in this part, and almost spherical and pressure supported galaxy in this part. The dotted lines represent the model with the same model, but seen with different viewing angle from edge-on to face-on, while the dashed lines represent galaxies with constant intrinsic ellipticities, but with varying viewing angle from face-on to edge-on. The main result is that the ages in galaxies seems to follow the location of projected intrinsic ellipticity, which is described by the dotted lines. Going from a dynamically cold and intrinsically flat into a dynamically hotter and pressure-supported thicker oblate spheroids, we can see that the mean age is increasing. The author found out that there is no dependency on stellar mass. In fact, they separated their sample into mass bins, and they observed the same general trend as before. Here they plotted the ages versus the intrinsic ellipticities in mass bins, and they observed a similar trend. In the last part of this slide, you can see the velocity over sigma versus ellipticity diagram, color-coded by mass. We have in blue low mass galaxies, and in red high mass galaxies. And as you can see, there is no dependencies on on mass. But galaxies with the highest stellar mass are more likely to be found in pressure-supported spheroids. Here. So the author underlined the fact that this new relation, goes beyond the general notion that disks are young and bulges are old. In fact, using the velocity over sigma ratio is a better tracer than bulge to disk ratio, which is difficult to measure because of inclination and dust extinction, and because secondly because bulge to disk decomposition show that there is a wide distribution in the Celsius index for both bulges and disks, and that bulges can be blue and disks can be red. Thirdly, they argue that optical morphology is not an ideal way to trace the dynamical structure for early type galaxies, because in many early type galaxies we can find high value for the velocity over sigma ratio. And fourthly, they underline the fact that they discovered the same relation between age and intrinsic ellipticity even in low mass galaxies, where there is a few number of classical dispersion-dominated bulges. So in order to be sure that their result is not affected by the wide range in morphology of the sample, they divided their analysis into early type and late type galaxies. In general, early type galaxies are older, more spherical and dispersion-dominated than late type. However, they found a similar trend in the two samples, which is similar to the previous one, to the general one, which tell us that young stellar population are in rapidly rotating, intrinsically flat galaxies, while older stellar population in more spherical and pressure-supported galaxies. Finally, they projected their result in the intrinsic ellipticity inclination plane. So you can see the intrinsic ellipticity and inclination, which is obtained using a theoretical model. Even here you can see that the stellar age followed the intrinsic ellipticity quite well, and there is no dependence on the inclination. Here on the right you can see the relation between age and intrinsic ellipticity for early type and late type galaxies, which are located in different position of the relation, but in the region, in the overlap region, both the two type of galaxies show similar values for ages and intrinsic ellipticity. So to summarize and conclude, thanks to their broad range in mass, morphology and environment, the authors could provide a strong constraints on how galaxies build up their stellar mass and angular momentum. From theoretical analysis, we know that bulge formation due to mergers and secular evolution processes such as bar formations can change the value of the ratio between velocity and velocity dispersion and the ellipticity distribution over time. So both the processes are expected to be able to explain the observed relation. In early type galaxies, this observed relation is consistent with the predictions and the observation for galaxies at high redshift, where massive red and dead galaxies are still rapidly rotating. So major and minor mergers can transform these galaxies into more spherical and more pressure-supported structure. And so we can this is in good agreement with the result. Then for early type galaxies. Then in the Milky Way, we know that there are two disks, a thick one and a thin one. The thin one is younger, and the stars are on circular orbit with a low velocity dispersion, while the thick disk is expected to be a combination of stellar migration and flaring from old disk stars. So this is in good agreement with the result of this study, where older stellar population are in intrinsically thicker structures. And for observation of the H alpha velocity dispersion, which is associated to star formation, we know that this velocity dispersion decreases with time. So, as the universe ages, we know that newly formed stellar population is expected to reside in colder rotation disks, and which is conforming with still with these findings. So, to conclude, in this letter, the author observed a relation between the intrinsic shape and the stellar population age, and they used a wide simple imaging spatially resolved dynamics in order to analyze their galaxies, and they underlined the importance of using integral field integral field survey to understand better the processes that are involved in building up the stellar mass and angular momentum in galaxies. So thank you.
Thank you. We have time for one question.
I don't have a question, but it's okay, not everybody can speak English perfectly. This is perfectly understood by everybody. And what I suggest is that we make an effort to try and pronounce at least the professional terms correctly, like mathematics and physics. And this is about the fourth time this year that I tell you it's not parameter. This word doesn't exist. The word is parameter. Sorry.
Okay, thank you.
I think it need, I think it makes it look so much more professional if at least the professional words are pronounced correctly. It gives a completely different impression. So please
Okay.
make an effort.
Okay, thank you.
Okay, thank you, Virginia.
Thank you.
So, see you next Monday, and next Monday. We're gonna have. Ok, bye bye. Perché c'è uno che sente. No, non sentiamo.